During a SEV1 production incident, an engineering team doesn't suffer from a lack of information. They suffer from an avalanche of telemetry. The moment a critical failure occurs, open telemetry metrics, structured logs, and distributed traces all spike simultaneously across the stack. The initial instinct to automate this chaos is to deploy specialized AI agents, a triage agent, a runbook agent, a remediation agent, and have them communicate directly with one another over standard REST APIs to resolve the issue. This node graph models a direct API architecture. When the triage agent and remediation agent send conflicting data requests directly to one another, they create a mechanical failure point. Without a centralized state, a single alert retry can cause the agents to loop continuously. Because the agents are calling each other directly, they rapidly hit internal API rate limits. Their internal states desynchronize. In trying to fix a database failure, the agents might accidentally open 3 separate Slack war rooms and trigger redundant PagerDuty alerts, creating a fragile, destructive spaghetti swarm. Without a centralized coordinator to manage state and strictly separate communication, adding autonomous agents to a production incident compounds the chaos rather than resolving it. The reliable alternative to the spaghetti swarm is an event-driven incident orchestration system. To make this work, we enforce one absolute architectural rule: autonomous agents must never communicate directly with one another. Looking at this diagram, we replace the tangled web with a centralized linear event bus, typically Kafka, NATS, or SQS. This bus becomes the single source of truth for the entire architecture. The agents operate strictly on a publish and subscribe model. They listen for state changes on the bus, perform their specialized tasks, and emit canonical events back onto the stream, totally unaware of which downstream agent will consume them next. Decoupling the communication through a message bus provides natural back pressure. If an alert storm hits the system, the messages queue predictably. The agents process the events at their maximum safe capacity without being crushed by the incoming load. Every incident starts at the telemetry plane. Open telemetry collectors route application metrics to Prometheus, push application logs to Loki, and export system traces to Tempo. When a system threshold is breached, Prometheus evaluates its alert rules and triggers Alert Manager, which fires an HTTP POST webhook secured via internal MTLS or an HMAC-signed header directly to the incident orchestrator. The orchestrator catches incoming webhooks in a funnel, deduplicating hundreds of identical alert payloads into a single fingerprint hash. This fingerprint anchors a correlation key, mapping the alert to specific metadata dimensions: service, environment, tenant, and cluster. With the event correlated, the orchestrator moves to persistence. It writes a durable state machine record, marking the status as new, into a centralized Postgres database. Finally, the orchestrator publishes a canonical event onto the message bus, officially handing the problem off to the agents. By forcing raw signals through this rigorous, state-backed orchestration layer, we prevent the downstream agents from wasting compute power on duplicate alerts. The publication of that canonical event initiates the wake-up sequence for the Agentic NOC. Specialized consumer groups like triage, comms, and remediation detect the new event on the bus. Notice how these 5 distinct agent nodes surround the central Postgres database. The bus payload alone lacks historical context, so every agent must query Postgres to pull the durable incident state before proceeding. Concurrent execution is a massive risk. We cannot have 2 agents creating separate PagerDuty incidents simultaneously. To maintain order, the system uses Redis for leader election. A short lock blocks redundant actions, ensuring only a single agent proceeds. The consumers store their last processed offset for every incident, utilizing strict item potency keys, so if a process fails, the action won't double apply. Relying on durable Postgres state machines and transient Redis locks allows the agent swarm to scale horizontally without losing operational singularity. Next, the system must prove the alert is actually real. The evidence agent queries Prometheus and Loki via their HTTP APIs to pull relevant metric snapshots and log signatures. Look at how these distinct data streams align. The correlation glue is the OpenTelemetry Trace ID. The evidence agent uses this string to cross-reference an error span with structured logs, mapping it to a specific latency spike, stitching them together. This correlated data is packaged into a human-readable JSON evidence bundle and stored securely in an S3 bucket. Concurrently, the runbook agent begins parsing organizational knowledge using retrieval-augmented generation, or RAG. During ingestion, Confluence pages and historical Jira tickets are split into chunks, embedded and indexed into a vector database like pgvector or Pinecone. The runbook agent queries this vector database, injecting the extracted log signatures from the evidence agent to retrieve highly specific, top-ranked mitigation steps. This evidence-backed proof package provides the context necessary for immediate decision-making. By delivering a verified diagnostic report alongside the alert, the system removes the manual investigation phase entirely. The limitation of standard threshold alerts is that they're entirely reactive. They only fire after the system is already failing and customer requests are dropping. We solve this by integrating a predictor module. Using anomaly detection on leading indicators, like queue depth or saturation, it generates advanced warnings before a threshold breaches. This secondary path shows how we handle early warnings. These predictive signals are injected into the orchestrator pipeline, explicitly tagged as risk. It bypasses the critical alert pipeline, but routes cleanly into the main Kafka bus for the agents. When the agents consume a risk event, they execute proactive mitigation sequences, like automatically scaling up deployments or preemptively warming caches, long before the users notice any latency. Routing predictive signals through the standard incident orchestrator enables engineering teams to preemptively stabilize their infrastructure, shifting the SRE culture away from reactive firefighting. Here is how that intelligence reaches the engineers. The comms agent triggers the agent-to-human layer, using deduplication keys to establish a deterministic Slack war room. This interface displays the structured incident card alongside direct links to the S3 evidence bundle. Immediately, the remediation agent publishes its hypothesized root cause, for example, database connection pool exhaustion, and presents a ranked mitigation plan inside the chat. This introduces the most vital safety boundary in the entire architecture. The agents themselves do not hold production Kubernetes or cloud API credentials. Instead, execution is handled entirely by the remediation gateway. This is a dedicated, isolated service that holds the execution credentials and physicalizes the separation between planning the fix and applying it. True automation safety depends on strict physical separation between the planning layer that proposes a fix and the execution plane authorized to apply it. The remediation gateway enforces strict policy as code checks before allowing any change. It validates per-service role-based access control, ensures the action respects blast radius limits, and executes mandatory dry runs. If the incident requires active mode remediation, meaning the proposed action is risky, like draining a node, the gateway holds the action in suspense. It waits for a human engineer to click an interactive approval button in the Slack war room. The moment the engineer clicks approve, the gateway logs the identity of the approver, disengages the lock, and transmits the payload. It uses idempotency keys during this exchange to guarantee the Kubernetes API doesn't double apply the change. Post-execution, the gateway monitors auto-stop conditions. If telemetry metrics worsen after the fix is applied, it immediately halts the automation and returns control to the engineers. Once the system stabilizes, the ticketing agent wraps up the process by creating a Jira ticket, automatically populated with the incident timeline and links to the evidence bundles. Finally, the postmortem agent pulls logs from the event bus to automatically draft a Confluence document detailing the root cause and suggested action items. By combining decentralized agent logic with rigorous state-backed gateways, organizations achieve scalable, autonomous remediation that SREs can actually trust.